Hello, I am Mohammad Adnan Faisal Hussain, and today I will demonstrate my implementation of a 4-bit computer on Verilog HDL. Here is my computer instruction sets. In total, there are 16 instructions. Now let us have a look at the block diagram of the computer. We have a 4-bit bus, we have a program counter, a 4 into 4 stack memory, a 16 into 4 RAM which holds both instructions as well as data, a controller that sends the control word. We have two registers, register A and register B. We have an input port and an output port. We have limited ourselves to 4 bits. As a result, the RAM only contains 16 locations and each location can only hold a 4-bit data. All the 16 binary numbers are assigned opcodes for instructions, and then as a result, there are no opcodes left to extract data from memory, as that would require 8-bit instructions. We have written test programs to test our code. The first test program tests the operations move, exchange, add, sub, push, pop, rotate, carry left, and halt. First, we have move A address. When instruction pointer equals to 6, at the very first positive edge of clock, register A is set to the value of 6, which is the value stored in address location 14. Next, we have exchange BA. When instruction pointer is equal to 2, the value of register A is set to 0, which is the previous value of register B, and register B is set to 6, which was the value of register A. Next, we have move A byte. When instruction pointer equals to 7, register A is set to the value of byte 10. Next, we have sub AB. When instruction pointer equals to 1, A is subtracted from B, 10 minus 6, and the result 4 is stored in A. Next, we have add AB. When instruction pointer is equal to 0, A is added to B, 4 plus 6, and the result 10 is stored in A. Next, we have push B. When instruction pointer is equal to 9, the value of register A is pushed back to the stack. We can see stack pointer changes to 1. So stack pointer now points to the memory location 1 of stack memory. Rotate carry left B. When instruction pointer equals to 11, the value of B rotates to the left by 1 unit and changes from 6 to 12. Next, we have pop B. When instruction pointer equals to 10, the value at the stack memory at which the stack pointer is pointing 6 is passed to B. The stack pointer is decremented by 1 from 1 to 0. Next, we have halt. When instruction pointer equals to 15, halt is set to 1, indicating the end of program. At the next negative edge of clock, program counter, instruction pointer, and stack pointer are set to 0. Next, we have test program 2. In this program, we test the operations in, out, and increment. We also check how the 0 flag changes. First, we have in A. When instruction pointer equals to 3, the value at the input port 8 is passed to register A. When instruction pointer equals to 1, both A and B have the same value of 8. At the first positive clock edge, sub AB is performed. Hence, the value of A changes to 0. Simultaneously, 0 flag is updated to 1. Increment A. When instruction pointer equals to 5, the value of register A increments by 1 and changes from 0 to 1. Next, we have out A. When instruction pointer equals to 4, the value of register A is passed to the output port. In our next test program, we test the operations call and return. We also check how the overflow flag changes. We assume the value of address to be 8, input to be 7, and byte to be 11. Call address. When instruction pointer equals to 12, at the first positive clock edge, the current value of PC 4 gets stored in the stack pointer, and the stack pointer gets updated to 1. The program counter value gets updated to the value address. When instruction pointer equals to 0, add AB, 7 plus 11 is performed. As the result is greater than 15, we cannot store it in a 4-bit number, and hence overflow flag is updated to 1. Return. When instruction pointer equals to 13, the program counter is set to the value at the stack memory at which the stack pointer is currently pointed 4, and the stack pointer is decremented to 0 from 1. Next, we have our test program 4. This is used to test the operation and also check how the sign flag changes. We assume the value of address to be 15 and input to be 11 and byte to be 14. And A address. When instruction pointer equals to 14, bitwise AND is performed between A, 11, and address location, which is 12. The result, 8, is stored in A. When instruction pointer equals to 11, A is subtracted from B, 12 minus 14, and as the result is negative, the sign flag is updated to 1. We also built an assembler which converts assembly code to machine code using Python. The assembler is only specific to the given instruction set. The code was written in Quarters 2 software. The 4-bit computer was successfully implemented using Verilog HDL. Different test programs were used to test the performance of the code, and it was seen that the computer is successfully able to perform all the tasks given in the instruction set. Thank you.